So all of our conversations about applications of integration so far have been very focused on three dimensions. We have spent a lot of time thinking about ways to find the volume of an object. Well, in this lecture, we're going to kind of take a step back down to one dimension and see how we can use integration to find the length of a curve between 2 points. So I've got a setup here for us to look at, just kind of a very generic arc, and I want to find the length of this thing between A and B. Well, to do that, I'm going to kind of continue the pattern we've been following in previous lectures. I'm going to think about dividing that interval from A to B into n subintervals. We'll see if we can't find a good approximation for the arc length on each interval, add them up, take the limit. Hopefully that'll get us a formula we can use. All right, so let's look at a subinterval here. Right? Let's look at this one. So what I'm going to do, I'm going to draw in a right triangle here. Right? I'm going to sketch this line across. Now, the base of this triangle, that's our delta x. And the height of the triangle, that's going to be delta y. All right, so now look at the hypotenuse of this thing. The length of that hypotenuse is a pretty good approximation of the length of the arc in that section. So what is the length of that hypotenuse? Well, it's just the Pythagorean theorem. It's the square root of dx squared plus, excuse me, not dx, dx is coming later. It's the square root of delta x squared plus delta y squared. So if I add up all those individual hypotenuses for all of my n subintervals, I get a fairly decent approximation for the length of that arc. Right? So my approximation is the sum I equals 0 to n, the square root of delta x squared plus delta y squared. Okay, it's got a delta x in it, which I'm kind of happy about, right? That turns into dx when we do our limit. I'm not so happy about seeing a delta y in there. Right? How delta y is changing as delta x does, that's, I don't know. So essentially I need to get rid of it. And here's how I'm going to make that happen. I'm going to use the mean value theorem. Remember, the mean value theorem says that if I pick 2 points on a continuous function, like the endpoints of my subinterval here, then there exists a point somewhere on that subinterval where the slope of the tangent line at that point, remember that's the derivative, is equal to the slope of the secant line being my hypotenuse. Okay, well, the slope of that secant line, that's just delta y divided by delta x. Okay, so the mean value theorem is saying that there exists a point c sub I, right? I've added that to the x-axis there. There exists a point c sub I on that interval such that f prime of c sub I is equal to that slope. All right, that's going to give me the tool that I need to get that delta y out of there. If we multiply the left and right sides of this by delta x, we get delta y is equal to f prime of c sub I times delta x. There's my substitution. All right, I'm going to substitute f prime of c sub I delta x for delta y in my approximation up there. So that becomes the sum I equals 0 to n square root delta x squared plus f prime of c sub I delta x, that whole quantity, squared. Okay, so I'm going to factor out delta x squared from both of these terms. And then we'll have the square root of delta x squared, which is just delta x. And so that makes my approximation the sum I equals 0 to n, the square root of 1 plus f prime of c sub I squared times delta x. And that's what I really needed to see. I've got the delta x on the outside. I've got no deltas anywhere else in there. So I'm going to just kind of do what we do. Right? I'm going to take the limit as n goes to infinity of that series. When we take the limit, the sum becomes an integral. Delta x becomes dx, and my approximation becomes the exact answer. And that right there is my formula. The square root, the integral from a to b of the square root of 1 plus f prime of x squared dx. Okay, so I've written that out here, right? Kind of just put our final conclusion. But there is one point I do want to emphasize because this is a little more restrictive than some of the things we've looked at before. In order to invoke the mean value theorem there, I had to know that the function has a continuous first derivative. Now, that's not a massive restriction. Right? Most any function you're ever likely to see in a practical situation is going to have a continuous first derivative, or worst case, you can split it up into individual components to do. So that's not a huge deal, but it is something we're going to need to keep in mind going forward. Okay, so now that we've got that formula in hand, we're going to take a look at some examples, see how we could use that with some specific functions.